There's been a lot of talk recently about how AI is slowing down at the frontier model level and how the gains are becoming less and less. And yet, while the effectiveness of scaling training is leveling off, the complement of this, or test time or inference scaling, is actually ramping up right now. And a lot of important discoveries are being made in this area, including the surprising effectiveness of test time training. Let's take a look. Hey y'all, it's Dr. Know-It-All. I've been wanting to talk about this article for almost a week now, but I've been very busy. And I also wanted to digest the article and really think about it. I think that this is a very important article. This is out of MIT by Ekurik et al. I hope I'm pronouncing that name correctly. And as I said in the cold open, it is entitled The Surprising Effectiveness of Test Time Training for Abstract Reasoning. This is an important article. As you can see, I have highlighted it and taken some time to read it. I'm going to go through and explain it to you, but of course I will skip over sections. So definitely check out the link to the original article in the description. It is very well written and very easy to read if you are familiar with this stuff at all. Anyway, I'm going to go through the abstract first, which of course is the TLDR of articles. So if you want to take a quick look at things, just always look at the abstract. Anyway, they say we investigate the effectiveness of test time training, or TTT, updating model parameters temporarily during inference using a loss derived from input data. Of course, I will go into what all this means a little bit later. There are three crucial components for successful TTT. One is initial fine-tuning on similar tasks. Two is auxiliary task format and augmentations, very importantly, augmentations. And three, very interestingly, is per instance training. And then the proof is in the pudding here. TTT significantly improves performance on ARC tasks, achieving up to 6x improvement in accuracy compared to base fine-tuned models. And applying TTT to an 8 billion parameter language model, in other words, Llama 8B, this is a very small language model, and this is one of the important aspects of this. This is competing at and actually state of the art at this point, given what they're doing with test time training. And that's in competition with models that are 2 orders of magnitude larger, like 400 billion or even a trillion parameters or more. So this is very impressive work that this team at MIT is doing. Now, obviously, this is not all unicorns and rainbows. There are still some issues with this, the biggest of them being time. But that's exactly the trade-off that many models are starting to do now, right? They're starting to transition from training scaling over to test time scaling. In other words, letting the model think for longer. This article discusses a more sophisticated version of that, but basically you're just giving the model more time to think. And you're doing it in a very structured way here. But anyway, that's the import of this, is that they're able to get amazing results from a pretty small model. And very importantly, on this ARC test, this ARC challenge, they got a validation accuracy of about 62%, which matches the average human accuracy on this task. So that is very impressive. Francois Chollet, I think he set this out about a year ago or so when he created the ARC challenge, but he said that this was something that large language models would never be able to do. Next token prediction would never be able to do this task. I looked at the task as I was reading this article. I'd seen it before, obviously, but never really thought about it. But as I read this article, I realized that he is dead wrong about this, because effectively this is just a complicated game of chess or Go or what have you. But the upshot is that you have simple rules that you can figure out. You can intuit those, and once you learn those rules, you can master a game like this. And again, I will talk more about the specifics of this in just a second. It will be obvious when I show you pictures. But once you master the rules of this game, it's very easy. The loss function is easy. In other words, whether you get it right or wrong is easy. This is much simpler than reality is. And so I think that large language models within the next year or so, using tricks like this, are just going to they're going to get 100% or very close to 100% on this test within a year. So I think Chollet and all who have staked their claim that these models will not ever be AGI because they can't solve a task like this are going to be proven wrong in less than a year. I think by the end of 2025, we will have models that are getting, in the 90s to 100% on this test. So with that uncontroversial statement out of the way, I love that, right? Anyway, let's get to the article itself. So we're going to start with this picture here, and actually let me blow it up a little bit so you can see it better. So here we go. We have some of these are examples of the ARC challenge, which is abstract reasoning corpus or something like that. I can't remember the exact, it's ARC, but it's abstract reasoning corpus or abstraction reasoning corpus. But anyway, what you're supposed to do is you look at these examples. So here's an example, and these are the results. So this is like the input, this is the output, and then they give you this and they say, what is the output? You're supposed to guess what the output is. You sort of rationally figure out, okay, all the outside corners are going to color yellow and the inside corners are going to color this sort of orangey, whatever color. So, you look at these two examples and yep, that works. So you've seen two examples and that's enough for you to judge. And then therefore you should judge this bottom one here. Of course, this is what the previous, large language models they're comparing to was guessing. And clearly it was wrong about that. It didn't understand it, but their version actually understands this. And again, at about 62% accuracy. So it's not 100%, but the average human is about 62% accuracy. The best human is somewhere around 98%. I think it's 97.8%. But anyway, the best human, they give them very complicated ones, of course, and those even the best humans can't get. So we're not 100% accurate, but I think that we are going to have these models are going to reach best human level of like 98% within the year. So anyway, many images like this make up the ARC challenge. So that's where we're starting from. So as they note, a significant finding in recent years, and this is very, very true, has been that large language model performance can be substantially improved by augmenting LM decoding with additional test time computing. And again, what they're going to do here is they're going to allow the model to look at these individual challenges and think about these challenges and actually retrain itself to do better on these challenges in order to get a much higher score than just throwing one of these images at something like ChatGPT or Grok or what have you. They will provide a few shots of examples, basically like we saw previously, right? This is like we have two examples and a human being. We figure out what the answer is by looking at these two examples, inputs and outputs. The Llama 8B model that they give, they show it a couple of these examples and they'll talk about augmenting the data, the samples and so forth by doing a few interesting tricks. But basically they're only giving it a very, very few of these examples. And if you compare that to the trillions of words or tokens that they train these large language models on, like all of the, the information, all of the words off of the internet, to train something on like a dozen of these examples, which you can get by augmenting these things in a way that's reversible so they can understand the ground truth of it. But they're basically retraining the model each time based on just a few examples. And it's actually rather impressive that they can create something that works so well with just so few examples. But of course, this is how we humans work. So if you think about it, if you have a general sense of tools and things like that, but you've never replaced a faucet in a sink, then what you might do is you might go to the store, of course, and buy the faucet and then look at the manual that comes with it, the instructions on how to do the replacement, then maybe watch a couple of YouTube videos or something like that. And so what you're doing as a human being is you're just adding on a little bit of a layer on top of, you already have all of your life experience and everything, which is the equivalent of the training that the large language model has previously done. But on top of that, for a temporary period of time, which is I need to replace the faucet in my kitchen sink, you add on top of that, you reweight your neural network a little bit in order to understand how to replace a faucet or something. Now, if you're a plumber and this is your job and you do it 3 times a day, then that's just part of your, that's part of your basic neural network. But for most of us who don't do that, we learn how to do a task like that and then more or less discard it after we get done working on that task. It's not important for our daily lives. You pick it up, you learn it, and then you discard it after you learn it. This is the same basic concept here. It's like, how do we do a test like this? Well, we do a test like this by learning how to do this test. So you take these examples, you augment it, and make a few more examples out of this that have the same input and output pairs. So, right, you could rotate this by 90 degrees, right? You could just take the whole picture and rotate it by 90 degrees, which is one of their augmentation strategies. It still produces the same thing. So you can augment this and go from 2 examples to like 90 degrees, 180 degrees, 270 degrees. So you go 2 and then 4 and then 6 and then 8, and then you can do some other things potentially like translate it around in the scene and things like that. So, you can get 10 or 20 examples out of this where you already know the ground truth because you haven't done anything fundamentally different to this. All you've done is rotate it or move it around. So you can get these examples, and that allows their test time trainer, their TTT, to learn how to do this. Same basic idea as how a human does this, of course, without all the swearing and, getting your like plumber's wrench into this tiny little space that's there, that's available under the sink and all that garbage, So anyway, I guess maybe the large language model in the background is swearing at this. I don't know, but this seems like plumbing and swearing are just the 2 things that go together because you're just always frustrated trying to do it. But anyway, that's the basic idea idea here is you're throwing out a few examples and it's just learning it for this purpose alone, for this example alone, and then it discards it. It goes back to its kind of base level understanding of things, and you train it for the new one, and then it learns how to do that one, and then it answers the question. And you can see that what you're doing is you're trading off time, of course, because at test time, instead of just going one time and saying like, what's the answer? And it just produces an answer, which takes very little time. You're saying like, hey, retrain yourself, learn how to do this thing, and then we'll ask you the question. So it could be orders of magnitude slower. And that's one of the main limitations that they have, of course, to this methodology is it's really, really slow compared to just firing it off and asking a large language model. And I'm going to get back to that at the end of talking about this article, because I think it's a critical problem with what they're doing here in terms of applying this to a more complicated solution, but I'll get back to that. So as they continue here, test time training in which models are updated through explicit gradient steps based on test time inputs operates in an extremely low data regime. That's what I'm talking about. Just a few examples and it's able to figure it out. That's pretty cool. Anyway, this stuff has been proposed for a while, but they didn't know what the best methodology for, making this all happen architecturally, training wise, etc. And then ARC is actually abstraction and reasoning corpus. Sorry, I got it slightly wrong. And of course, Chalet et al. Were the ones who developed this about 5 years ago. So here's how this all works. Number one, they do initial fine tuning on synthetic tasks similar to those encountered at test time. So they take their base Llama 8B model and they fine tune it to already basically understand these questions, right? The basic kind of graphical thing where you give it a grid and you say, here's an input and here's an output, here's an input, here's an output. They train it how to understand how to do these things. Not the specific tasks, of course, because that would be cheating. Then it's just memorizing. But they basically say like, okay, we're going to give you a head start so that you already basically know. So it would be that same sort of thing, again, if you were going to do plumbing under the sink. If you have already done other plumbing jobs in your life, not that you have to be an expert on it, but that's going to give you a leg up and you're going to be able to do it more quickly and with more efficiency and with fewer leaks and things like that than if you had never replaced a sink before. The first time you do it in your life is always one of those like, whoopsie, this is not as simple as I thought it was. Then they got on to step 2, which is an augmented leave one out task generation strategy for constructing test time data set. That, again, like I said, is that augmentation of rotating and translating and moving things around in the scene, which doesn't change the ground truth of the input and output pair, the input and the answer, but it effectively makes the data set larger than it would have been because 2 examples is just not enough for these language models to learn on, apparently. For us humans, we can do it. We look at it and we're like, oh yeah, I got it. I understand. But for these models, they don't understand how to do that. Then 3, very interestingly, is per instance adapter training. And in other words, they build a LoRa or a low rank adapter. In other words, some stuff that goes on top of your base models, some new numbers that get multiplied through as it works on the problem that allows it to basically ultimately fine tune itself on this one individual task. And then they throw that LoRa away when they get done with that individual task and retrain for the next one. So you can see why number 1, it would be much better because it's specifically trained for that task. But number 2, how that's not very generalizable. And there's a huge waste of time because you're training each of these LoRas and then chucking it. You're not using it. So they have a huge advantage in terms of the accuracy of this, but a huge slowdown. And because they're just wasting all of this effort for one question only. And then 4, they talk about self-consistency under invertible transformations. I think that's just part of their data augmentation. Honestly, that, in other words, is rotation and translation and stuff like that. So I don't know why they have that as a step 4. It seems like a step 2. But anyway, whatever. That's their step 4. And then down here, they say with an 8 billion parameter model, our results show that when equipped with test time training, ordinary language models can match or exceed the performance of many neurosymbolic approaches on ARC, which are the state of the art at this point. So we'll skip a bunch of text here and just move to this picture, but you can see that we have an original task here with the question, and these are columns, and clearly what you've got is if it's in the bottom, like row at the bottom here, you go up 1. If it's in the middle row, you go up 2. And if it's in the top one, so basically you're kind of filling it in underneath, I guess would be the way to look. But what they've done is they've taken these original 3 data sets. In other words, they've got 3 example input and output pairs. And you can see here, they've done a horizontal flip. Here, they've done a vertical flip where it's actually upside down. And then that produces a new data set so that they have effectively augmented data, but they still know what the correct answer is. And they can then use this by leaving one out at every time, right? So they generate 2 and they leave the third one out. And then the model is either being fine-tuned on this originally, or if it's this specific problem where you want an answer in the end, then what it does is it learns a LoRa for that specific problem, which is effectively just tweaking all of the neural network weights just a little bit at a very low order, which is why it's called a LoRa. But anyway, it does that. It learns how to do that, and then it's asked the final question, which it hasn't seen before, but it's able to produce an answer because it's seen the example data set, expanded out to somewhere around a dozen or 20 or so examples. And then, like I said, very importantly, after generating predictions, the model is restored to the original parameters, which are already fine-tuned, but they throw away that LoRa that they use for that specific question. So for their testing, given how slow this is, they only picked 80 of the, I think it's 1,000 ARC tests, but they did 20 easy, medium, hard, and expert tasks, so they ended up with 80, but it's an order of magnitude less than the challenge, the full challenge. So this is a problem with their methodology because it just takes too long for them to create the answers. And that's not a workable solution. You can't trade off that much time for something like this ultimately, but hopefully what will happen is over time, we'll figure out ways of refining this and making this all work much more quickly. And then they do an ablation study, and ablation is one of those words like stochastic. Stochastic just means random. Ablation just means taking things away. So your original fine-tuned model only gives you 5 answers correct out of 30, whereas the one with the test time training gives you 29 out of 30, which is great. That's about as good as you can get theoretically. But then what they do is they take away different parts. So they take away the transformations, in other words, the augmented data set. Without that, they only get 13. And then, of course, through other ablations, they get rid of different things, and they use a Q-LoRa, which is a quantized LoRa, which reduces the resolution of the numbers of the LoRa, things like that. So anyway, they do a bunch of studies, but ultimately they're able to get 29 answers, which is pretty darn good. But ultimately, the really, really big discovery here is that instead of using a single LoRa, instead of training on all of these different examples in a generalizable way, what they do is they learn individual task-specific LoRas adapted for each task. In other words, for the 80 examples, they learned 80 different LoRa adapters, which is very inefficient, but also worked really, really well. And then I'll pause on this briefly. This talks about their hierarchical majority voting, which allows coherence between different examples. In other words, the voting allows it to be self-consistent because it's always voting on the best answer. So what they're calling this here, this inference strategy, they're calling it augmented inference. Recent work has shown that scaling test time compute can significantly improve the performance of language models. One of the most common techniques to do this is by sampling multiple responses and then selecting the best response using a ranker. However, while sampling is very effective in domains with multiple possible solutions, in other words, programs and code and stuff like that, or multiple possible paths to the final answer like math, it can be detrimental when generating answers directly, as there is no way to directly enforce diversity across samples while ensuring coherence within samples, in other words, the voting kind of thing. As an alternative to inference time scaling, we use an augmented inference strategy that generates multiple prediction candidates by using geometric transformations combined with a greedy decoding scheme. And then, of course, they show their results again. They show that using these different transpositions and things like that, you get various results. They are not as good as something that's aggregated, in other words, a flattened voting system or a hierarchical voting system. In other words, a first past the post voting system here is flattened, or you do a hierarchical voting system. You do a first round of voting, second round of voting, etc. And then the oracle is basically, if it produced the correct answer in any of the possible answers, it says that is correct. So that's sort of the best possible performance it could get based on the fact that it's able to predict in any of its possible answers the correct answer, and it gets pretty close with hierarchical. And then they get to their conclusion in which they say, we find that learning task-specific LoRa adapters and generating augmented test time datasets using geometric transformations, in other words, just rotating and translating things like that, are crucial. We also develop an augmented inference pipeline that uses invertible transformations to generate multiple predictions and then uses self-consistency to select the best possible candidates, in other words, voting. Our overall pipeline applies multiple test time computation methods, with each component contributing positively. This suggests that not only can test time compute improve language model performance, but different test time methods can also complement one another. So basically strategize first, but then throw a lot of compute resources at the actual test time compute. And then we get to the limitation that I alluded to earlier, that is to do 100 tasks of this ARC challenge takes 12 hours on an A100 GPU with Llama 8B. So this is a really, really cool insight into how ARC is going to be defeated. Again, Chalet and others said that this was never going to be defeated because language models just were not able to generalize, they could only memorize. And here this is basically a proof of concept that they are able to generalize if you give them enough information at test time, if you allow them to think about this in the right way and for long enough. So this is a really cool experiment, but highly, highly inefficient, right? Because you're throwing away this LoRa. You're spending all of this time to retrain the model just to do a specific task and then discarding it completely so it's not able to absorb that information into itself. Now, of course, you could try doing a generalized LoRa where you threw all of these examples at it and allowed it to train on all of those, but the problem is that that reduces the results because it's not specific enough to an individual task. But here's the thing, in the real world, there are lots and lots of edge cases that people talk about. In other words, self-driving, Tesla's full self-driving, things like that. You have weird situations that only arise once in a while. And this is where one of these little LoRa's might be really useful. If you think about taking a fine-tuned model and then training it with a lightweight LoRa on top of that, and then somehow caching that thing so that you know when to call that up. So to go back to our plumbing analogy, if this, computer could somehow do plumbing, I know you need a robot to do that, but if it could do that, it would just say like, oh, I've done plumbing before, and it would recall that LoRa for like replacing a faucet under a sink and put it on top of itself, which completely gets rid of the need to do data augmentation and to train that LoRa from scratch in order to do that. So if you have a way of caching these LoRa's, which are relatively small, and they just kind of sit right on top of the model, so no big deal, you can just slap them on top whenever you want because they're multiplied in with some of the weights. If you had an effective way of recalling that LoRa when you needed it, you could just slap it on top without re-incurring that test time compute. All of that extra wasted effort wouldn't be wasted anymore because you would have it sitting over there. So again, it's one of those things, like as a human being, we can kind of do that. It gets fuzzy after a while, right? If you've replaced a sink and a year later you have to do it again, you're probably back to square one. You don't really remember that much. But if you just did it a couple of days ago, you can probably remember it. So that's the kind of thing where you can pull that LoRa back in, the analogous thing. You pull that back in, you put it on top of your original fine-tuned model, and you allow it to work on the problem, and it should be able to solve that problem very, very quickly because it's just utilizing that model that it already expended the effort to learn how to do. So I think that that would be a really, really genius way to sort of bootstrap this system into a more efficient system that could then be reapplied to similar situations that it sees again. And that would be really, really cool. So overall, this is a really intriguing experiment. I think it's a fantastic insight into how these more complex generalization problems are going to be solved. Right now, it's not very efficient. It uses too many compute resources to do what it needs to do. But I think over time, there will be refinements, including remembering and caching these LoRa's and stuff that will allow these systems to operate very, very effectively and efficiently in the future. So those are my thoughts on the topic. Let me know what you think about all of this in the comments. While you're down there, if you don't mind liking and subscribing, it would really, really help. I would love to get to 100,000 subscribers by my 60th birthday at the end of January. So hitting that subscribe button real quick would really help me out, and I will see you in the next video. Bye-bye.